Now that we have a list of basic functions, we want to look at how we can create new functions from those. And so what we're going to do here is we're going to look at what's called transformations of functions. So there's various shifts and stretching and such that go on that allows you to create new functions. So what we have in this first one is what's called a vertical shift. So if I take a function and add something on the outside, it will shift the function up or down. I've only got the plus there, but let's look at an example. Suppose I take the function f of x equal to x squared plus 2. If I were to draw the graph of that, I know that the basic function is f of x equal x squared. We know that that graph would look like this. It would just be this parabola. But the plus 2, what it's doing is it's moving all the y coordinates up 2 units, right? I'm calculating my y coordinates, and then I'm adding 2 to each one of those y coordinates. So that has the effect of moving the entire graph, shifting it vertically 2 units. So this vertex is going to go to 2, and then I just see my parabola, same parabola. You can see that has the effect of shifting the range. The domain's still everything, but the range got shifted up by 2, so it changes the features some, but it does allow me a quick way to sketch new graphs by knowing my basic graphs. And it works if I have it the other direction as well. So suppose I have the square root of x minus 1, then that shifts that square root graph down 1 unit. So my basic square root graph looks like a sideways parabola, at least half of a sideways parabola, and then I'm going to shift it down 1 unit. So this is now going to be down here at minus 1, and then you see your square root graph. Supposed to be the same looking graph. This again does shift the range down. All the y coordinates got shifted down, so we'll change the range a little bit. But I can do that to any function. If I know the graph of something and I add or subtract something on the outside, it'll shift it up or down after I sketch the original graph. Okay, that's vertical shifting. We do the same thing horizontally, except what has to happen is the addition or subtraction has to occur on the inside of my function. So let's look at something like f of x equal to the absolute value of x minus 1. So my basic function here would be the absolute value function, and that would be this, that phi shape. But now this minus 1 on the inside is shifting it 1 unit. So let's see, what's it saying? It's saying that when I plug in, normally on my absolute value function, if I were to plug in 0, I would get 0. But this is saying, well, before the absolute value function thinks you plugged in a 0, you actually have to plug in 1. So it's right there when it thinks you plugged in 0, because it sees only what happens after the 1 goes in and you subtract it. So that moved this point to here, and it does that for every point. So if I were to plug in 1 here, then I would get a 1 out. But to get a 1 out of this, I'd have to plug in a 2, meaning I'd have to reach over here, plug in a 2, then it thinks I plugged in a 1. So it just takes the graph and shifts it. But notice it's shifting it the opposite of what that sign is. It's shifting it 1 unit to the right. So if I have something like f of x equal 2 to the x plus 1, that's happening on the inside of my exponential function. But what that graph would do, so here's my basic exponential growth. And then if I want to add 1 on the inside of that function, it's actually going to reach back 1 unit. So normally on a f of x equal 2 to the x, if I plug in 0, then I get 1. Here, I got to reach back to negative 1 before it actually thinks I plugged in 0. So it's going to reach back here, and then I'll get my 1. And so the whole effect is that it shifted it back this way 1 unit. So that's a shift to the left. So again, that opposite sign of which you expect, a plus 1 shifts left, a minus 1 shifts to the right. So that's your horizontal shifting. Next, we have stretching and compression on the vertical direction. And so what I get here is, the best graphs for those are the trig function. So if I take the function 2 sine x, what that does is I get my normal sine graph. Got it in blue now. So here's my normal sine graph, this a 1 period sketch of it. But then all of those y coordinates are getting doubled. So if I want to do a 2 sine x, then that point's going to be twice as tall. Every point's going to be twice as tall. The ones that don't change are the ones that are already 0, so those are going to still be there. This is going to be twice as tall, but in a negative direction. And so what it has the effect of doing is taking your graph and stretching it out in the vertical direction. So now it's going to stretch from -2 to 2 instead of just -1 to 1. And if I do that on the inside, and if I do 1/2, then obviously it compresses it. So that's when you're less than 1. And if I do it on the inside of the function, let's say I do cosine of 2x, then what happens, here's my normal cosine graph. This is 0 to 2 pi. But inside here, when if I'm doubling the x, that says that for me to for the function to think I plugged in 2 pi, all I really have to plug in is pi. So I can see that if I'm plugging in pi, then this function actually thinks I've already plugged in 2 pi. So it's going to give me the output that I would get at 2 pi instead of what I've got at pi. So that has the effect of taking all of these coordinates and compressing them down. It goes through my cosine graph twice as fast. And my outputs are still the same. It's just I see my cosine graph in half the time and half the interval. And so what that does on a cosine is it changes the period from 2 pi to 2 pi divided by that. So whatever number's there, it's going to give you that sketch in that time. And that happens for all the functions, just the sines and cosines are easier to display it, that compressing and such. If I have a graph that looks like, say, this, which is a semicircle, which I didn't put in our basic functions, but we'll deal with semicircles. You probably ought to remember them, that the graph of a semicircle looks like this. It's 1 minus x squared. The circle itself is not a function. X squared plus y squared equal 1. That's not a function. But when you solve, if you want the top half of the semicircle, you do square root like this. So anyway, that's a semicircle, and it goes from -1 to 1. But if I multiply on the inside, 1 minus 2x squared, then what that does is it compresses it by a factor of 2. And so minus 1/2 to 1/2, it gets crushed down, and I see my semicircle trying to be drawn in that smaller interval. Anyway, so there are other functions that it does work for, but it's easiest to show that on the sine and cosines. All right, the next transformation is a reflection. This minus, all it's going to do is change all your y coordinates. So the graph of minus x squared, here's your normal x squared, minus x squared, all it's doing is taking your y coordinates and making them negative, so it's just going to flip it over. So that one's pretty easy. If I have a graph like this, and I say that's the graph of f, if I want to draw the graph of minus f, what I do is I just flip all these over. That goes up, this will now come down, and then it'll cross there because it's 0, and then this will go back up, and then it'll come back down. And so you can see it's a mirror image when I can flip all the y coordinates, just flipping that graph across the x-axis. All right, the next one is we have this stretching and compression on the inside, which is actually, I already went over that. That was the one I did with the cosine. So I'm sorry, I kind of got ahead of myself. So this on the outside was the one that I did where I did the 2 sine. And then the stretching, compressing on the inside, I did the cosine. And you can see on the inside that 2 actually compresses it. On the outside, that 2 stretches it. So they kind of have that opposite behavior again. And then again, I did this. So now let's look at the horizontal reflection. And we'll take this function. Now I've got the minus on the inside. And what that's saying is, here's my normal square root graph, but it's only defined for positive. So this thing won't be defined except for negative value. If I put a negative in and then take its opposite, then I can take a square root. And so what it does is it reflects that graph across the y-axis. So up here, the minus reflects across the x-axis when it's on the outside. When a minus is on the inside, if you know the basic graph without that minus, then just draw that basic graph flipped across the x-axis. All right. The last one, we got a couple here, but we use this one, this number 7 more. The absolute value applied to a function. What it's going to do, let's just do it first by a graph. If I give you this graph, and I tell you I'm applying absolute value to it, then all the absolute value is going to do is take negative values and make them positive. These positive values it's not going to do anything to these. These are already positive, so the absolute value to all these y's are still going to be the exact same values. These are all still the same. The ones that are going to change are these. Because they're negative, the absolute value is going to turn them around and make them positive, so it's just going to flip that part up. So that blue graph would be the absolute value function. And so if I give you a function, now as you can see in this one, I can combine my different transformations. So here I've got my x squared graph shifted down 1 unit, and then I'm going to apply the absolute value. Well, let's see, the x squared graph looks like this. Then I'm going to shift it down 1 unit, which moves it down here, and then I'm going to apply the absolute value to that. Well, the absolute value is going to leave this part alone because it's already positive. It's going to leave this part alone because it's already positive, but it's going to take this part and it's going to flip it up and make it positive. So it puts this little weird bump in it, which was corresponding to the original bump down there. So that's what the absolute value applied to it does. The last one we don't use much at all. It's kind of a cool one. When I put an absolute value on the inside of a function, what that does is we can refer to that sort of as a cloning function. So suppose I have this graph, something like that. What the absolute value will do on the inside of this function f here, so this is my function f, you see that when I plug in x's, the function thinks I'm only plugging in positive x's, even if I plug in the negative. So when I plug in positive, it's still going to give me this same graph here. But on this side, what it's going to do is it's going to give me a copy of these. So when I plug in this value, it thinks I actually plugged in this value. So it's going to give me the same values from this side that I'm already getting on this side. So it's just going to kind of clone itself. This is my best try trying to clone itself. So it's going to make a picture of itself on the other side. We don't use that one much, but like I said, it's kind of a cool transformation. But we use these others, and we can use them in any number of combinations to create new functions. I've just used a couple on this one, but we could have 3 or 4 of these all together. And you probably saw that in trig when you did something like f of x equal 2 sine x minus 1, and then you add 2. So this changes lots of different things. It stretches it out, it shifts it over, and it shifts it up. So just be prepared that you can have several different transformations at once.